So welcome. We're going to start, I think. Scott, if you're ready. It's okay for you? Okay. So welcome everybody to this 15 webinars of IFC. The topic of today will be devoted to timber structure strengthened with FRP material. I would like to thank Scott Smith to accept to present and prepare this session. Scott is a well-known professor in Southern Cross University in Australia. And then for the session, if you want to ask any questions, I think the best way is to keep it for the end of your webinar. You can ask your question in the chat area, where I think it's the best place to answer, since if we open your microphone, I think we'll have it's quite complex to have discussion with a lot of people in the same time. So at that time, I will shut down my microphone and my video, and Scott, it's up to you to start your webinar. Thanks again for your contribution.
My pleasure. Thank you, Emmanuel, and greetings wherever you are around the world. Hello from Australia. I'm based up near the Gold Coast, which is not too far from Brisbane. Today I'm going to be sharing with you my experiences, my interest in timber engineering, and also research projects that I've been involved in, that I've supervised over the years around the use of FRP composites with timber. A bit of a background about myself. I started researching in FRP composites in the late 1990s. And a lot of my work over the years has been the application of FRP to concrete, and in particular the bond behaviour, the interfacial behaviour, and in more recent years, well, since about 2007, I've been looking at the use of anchorage devices to enhance the capacity of the bonded interface between the FRP and the concrete. So to increase the strength of the interface, but to also increase the deformability. And if we have experience with bond of FRP to, say, concrete joints, we would know that the bond strength is limited. It's limited by the strength of the concrete. And the bonding, which is the primary failure mode, occurs in a rather brittle manner. Hence my interest in anchors. Now, timber. I've been teaching timber engineering for quite a few years, for over 10 years. I worked for a few years about 9 years in total in Hong Kong, and developed an interest in historical structures, in particular timber historical structures. Hence my interest in the application of FRP to timber as a way to retrofit, repair. Originally it was historical timber structures, but now it's moved into just timber structures in general. And I've been able to use a lot of my experience over the years gained with FRP to concrete and apply that to FRP to timber. So the presentation today, I'm going to, after I give a brief introduction about the application of FRP to timber, work I've been involved in with regards to the strength or the behaviour of the bond between FRP and timber, namely through a series of joint tests. Then proposing a bond strength model that we can then use to design beams, or beams that have been strengthened with FRP with. And finally, I had another project on the strengthening of timber frames, in particular moment-resisting timber joints. The motivation there was to strengthen, to repair, to retrofit frames that are subjected to seismic attacks. And finally, some concluding remarks, where I think we have come from in this field and where we should be heading. In terms of an introduction, there's a lot of timber structures around the world. It is one of the oldest and the most popular construction materials. Historical structures we can see on the left, There were temples and gates, which can be found in Asia. And on the right, in my home country, Australia, timber rail bridges, or timber bridges. This was a dominant construction material over 100 years ago, in the mid to the late 1800s to the early 1900s. Considering that Australia has been settled by Europeans at least for over 200 years, timber, a readily available resource in Australia, was the primary construction material of its time. Now, there's a lot of timber bridges still in use today. So, by interest in the application of FRP composites to repair, to rehabilitate historical structures, but also timber bridges, which are used in Australia. And there's countries around the world which have a strong timber industry. Scandinavia, for example, Canada, and there's other countries around there. And a lot of timber structures around the world in use. Now, there is an Italian design guideline which was published in 2007, which the last time I checked was still freely available on the Italian National Research Council's website. This was one of the earliest and still one of the very few design guidelines around the world dealing with the application of FRP to timber. So what we can see in this picture is a photograph or a picture taken from this guideline showing the different ways that FRP can be applied to the cross-section of the timber. They're rather standard techniques, well-known, intuitive, if you're working in the field. You can see my little red pointer there. There's a more traditional technique of bolting or attaching well-defined structural shapes, such as a steel I-beam to a timber beam, or the more elegant FRP solutions. We have externally bonded plates, which could be along generally the tension face of the structure, the angles around the two bottom edges of this section. Here we have so-called near-surface mounted FRP. So the near-surface mounted involves saw cutting a groove along the length of the timber member, adding epoxy into that saw cut, and then inserting an FRP rod or a strip. In this case, it's a rod. And over here we have strip elements, more strip elements, and also a section shape there, and here surface mounted applied to the side region. The benefit of near surface mounted here is that it can be used to repair, to retrofit historical structures very nicely. The FRP is embedded within the section, and the exterior of the timber can be patched up or reinstated with the original timber, so you wouldn't know there's any strengthening in there. To point out, with historical structures, it's very rare and usually impossible to replace the original timber or the original species or grade of timber from a forest, from a plantation. Hence the reason for the application of FRP as a retrofit. So some of the research questions that we can ask for the application of FRP to timber. We're interested in the strength of the bond, behavior of the bond. When we understand the behavior, when we can quantify the strength, then we can design the application of FRP to timber. We can perform bond strength tests, and then we can upscale to incorporate FRP into actual structures. So this is not uncommon to the work which has been conducted over the years on FRP to concrete. And there's also been the application of FRP to metal and FRP to masonry structures over the years. So in fact, we can borrow a lot of learnings from the application of FRP to these other common construction materials to timber. I would say the application of FRP to timber has enjoyed the least amount of research. So if you're a researcher in this topic, there's a really ripe topic to perform some fundamental research and establish a reputation in this area. If you're a practitioner, then there is a suitable body of evidence and a growing body of evidence and design guideline to help you design FRP strengthening for your timber structures. So a background about timber. As I said earlier, it's probably one of the most common construction materials. Well, actually, concrete is the second most consumed material on the planet after water. But I would say timber has been used a lot longer than concrete. And there's a considerable number of timber structures around the world. Timber is comprised, its microstructure is comprised of cells, fibres, mainly in the longitudinal direction. Cells bounded together by rays. It generally has the highest stiffness, the highest strength, parallel to the grain. Timber is an anisotropic material, and as we can see here, timber sections are cut from trees. Trees, you should recall, grow each year. Each year there's an extra growth layer added to the trunk of the tree, say, and that growth layer will, depending on how the timber section is cut, will be reflected in the shape of the sawn timber. If you've got any questions, please feel free to put them into the chat box. So timber, again, as a construction material, what are the factors that we're most interested in? Well, the species of timber, whether it's a softwood and a hardwood, and so examples here are pine and oak, respectively. The moisture content, whether it's seasoned or unseasoned. So unseasoned, there's still a reasonably high level of moisture in there. Seasoned, the moisture is brought down to an equilibrium content of around 12 to 15%. Direction of the grain is important, the density of the timber, and also the natural growth characteristics. So common characteristics are knots, checks, pips, and corewood. Timber is a notoriously variable material, made notorious by the natural growth characteristics. Steel, by comparison, is a much more uniform material, and masonry and even concrete to a degree. A bit more of a background about timber. This is an excerpt. This is one of the key tables for the design of timber, and this is taken from the Australian Standard for Timber Structures Design, published by Standards Australia. We classify timber in terms of its stress grade and F grade, and so an F grade ranging from F4 up to F34. And we can see here the corresponding properties in bending, tension parallel to the grain, shear and also the compression, and the elastic modulus. So for example, an F8, which is a common product, has a tensile strength of 13 to 15 MPa, whether it's soft or hardwood. Compressive strength of about 20 MPa, and an elastic modulus of around 9,000 MPa. So comparing to other construction materials, concrete, elastic modulus is around 30,000 MPa, and strengths can range from 10, 15 very poor quality concrete to 100 plus MPa, high strength concretes. Steel, elastic modulus of around 200,000 MPa, and strengths from 250 MPa to higher strength steels. Now, the higher stress graded timber, which are generally not available anymore, but the hardwoods, the softwoods, MPa, tensile strengths of 50 to 60 MPa, and compression of 75 MPa. So these are some really strong woods that these higher stress grades were readily available, at least in the early settlement days of Australia, that timber railway bridges had been constructed out of. There's been some interesting research I've seen done in recreating these higher stress graded timbers out of composites or hybrid timber composite materials, which could be used as a replacement for timber, but which exhibit the same strength and stiffness characteristics. Moving on to FRP, it's a brittle material, as we can see from this stress-strain response in the top right-hand corner. Glass and carbon being the common fibre materials. Aramid is less common these days. There are other fibres coming onto the market, various degrees of activity of basalt and even hemp. You have commercially available products of strips and sheets and tendons and even whole protruded sections. For my work with timber, we have been concerned with the use of protruded plates, as well as fibre sheets. And rods, flat strips can also be used for NSM applications. The epoxies that are available on the market and are generally used by researchers and applicators around the world, and what we have used in our research are Cicader, Typho, and Arodite products. You can see some of the main characteristics here as provided by manufacturers. Normally allow 7 days curing time, elastic modulus of 2,000 to about 11,000 MPa, so a weaker timber there, equivalent, and elongation at rupture ranging from 0.9% up to about 9%. Now, when we combine FRP to timber, what are the research questions we should be asking ourselves? And what's the effect of the various parameters on the behaviour, the strength of that bond? Well, there's the properties of the timber, its species, the direction of the grain, its density, its moisture content, etc. There's the actual FRP. There's the shape of the FRP and how it's used. Plates for externally bonded, rods, strips for NSM, the type of the fibre, carbon, glass, aramid, or other fibres, the type of the resin, the epoxy, the elastic modulus of the material, the geometry. These FRP questions have been asked for the application of FRP to other materials as well over the years. So for the adhesive, the type of the adhesive, its elastic modulus, the direction of the loading and the type of the loading. So with timber, we're also concerned not just with parallel to the grain, perpendicular to the grain, monatomic versus cyclic loading, surface preparation. This is important for the application of FRP to any material. But for timber, we would generally sand the surface of the timber. We would not apply a needling device such as that we would apply to steel, concrete, or masonry. But then with sanding, you ask yourself the question, what grit sandpaper would be used, for example? We don't want to go too rough, we don't want to break too many of those surface fibres, but we want to remove any surface impurities or weaknesses in the timber layer. And finally, the durability, in particular, the changing moisture condition of the timber is a real design issue. Because if your timber is like, if you're dealing with a seasoned or an unseasoned product, if it's located in an indoor environment, air conditioned, so it's nice and controlled, a nice uniform moisture content. But if it's an outdoor structure, or it's a structure where moisture levels can vary, this can lead to dimensional change. For bonded FRP, this could lead to stresses being induced due to this dimensional change. So to help answer these fundamental questions, we conducted a series of tests on joints. Now, what I'll show you here is a summary of one of my PhD students' projects, where she tested 96 NSM FRP to timber joints and also 195 externally bonded. Other researchers have also conducted such tests. But I'll present the findings of our tests. They're uniform as much as possible, and the variables isolated are for the NSM, the bond length, the adhesive type, the timber species, and we're also looking at the engineered timber species. So engineered timber, for your information, is blue lamb or LVL products, opposed to wholly sawn timber sections. For the externally bonded series, we looked at bond length, adhesive type, adhesive thickness, the FRP type, timber species, and also looked at engineered timber products, as in glulam. Now, the adhesive type, the bond length, these are all real fundamental properties which researchers have investigated for FRP to concrete, steel to masonry over the years. A matter of time before we had to look at these for FRP to timber. These photographs here, we can see a typical externally bonded joint on the left, and on the bottom right, an NSM strip embedded in timber. And having a closer look on the next page, see our NSM strip has been embedded into the timber. This is our typical test setup, which is not too unlike a lot of other bond strength test setups. It's a single lap shear test setup where the green frame is holding the timber block and the FRP strip, which is protruding from the timber, being gripped by the jaws of the universal testing machine. It's an easy test setup to remove the specimen, put a new one in, connect the various instrumentation devices, and test to failure. Here we have a configuration for the externally bonded test in plane and elevation, and with a series of strain gauges bonded along the length of the FRP. We also use cameras to detect the variation of the strain on the surface of the FRP. But I'll just present the results here from the strain gauge results, which were reasonably reliable. Now, preparation of the specimens involves a light sanding in photograph 1. In photograph 2, a cleaning. Typically, we'd use acetone. 3, the application of the FRP. Here, a student is applying FRP in a wet layout manner. So you can see the epoxy being rolled onto the FRP sheet. And finally, there's our finished product. So quite a short bond length for these ones. So we performed at least 3 tests for each configuration. And if there was considerable variation in the results, then we performed more tests. Here is the arrangement for the NSM configuration. So we've got a 1.4 millimeter wide strip of 15 millimeters deep. Strain gauge only attached to the exterior of the FRP. We haven't attached anything within the length of the bond. We didn't want to disturb that bond region. In the NSM and the EB tests, we've also used LVDTs to measure the slip taking place between the FRP and the timber at the loaded end of the joint. So from this instrumentation, we can record the level of strain in the FRP and also the distribution of strain along the length of the plate for EB. We can measure the slip at the loaded end of the joint. We've also got the load. And so from here we can extract some real fundamental and useful properties about the behavior of the bonded interface. Here is how we prepared the NSM specimens. A saw cut along the length of the FRP, cleaning out that saw cut, flushing with air, epoxy, and inserting of the FRP plate, and finally, in photograph 4, the test specimens ready to test. We tested the timber. So here are our properties for the softwood, the hardwood, and the glulam. Parallel, perpendicular to the grain. We've tested in accordance to a British standard 408. Softwood was pine, hardwood camphor wood, sourced from South China. Moisture contents, so it's the 9 to 14% mark, which is consistent with seasoned timber. And we can see the difference in the properties of elastic modulus and compressive strength, perpendicular and parallel to the grain. There's a big difference perpendicular and parallel. Properties of the FRP. We used wet layout, so sheets for the externally bonded application, as well as protruded plates. And we also used protruded plates for the NSM. These tests were conducted in accordance with the ACI 440.3 test document. The elastic module and their carbon so the elastic modulus around 200,000 MPa is consistent of carbon, tensile strength, as well as the elongation and rupture. We also tested the epoxies. So in accordance with an ISO 527 code, the latest version we had was 1999. So the preparation of dog bone specimens, we've tested 6 different types of epoxies, 3 different types of Sika, 2 different types of aridite, and a typho. Now the epoxies that we chose are the ones that have been commonly used in FRP systems for strengthening of either concrete, masonry, or timber. We did not look at any specific timber bonding agents in this study. We were interested in the commercially available products that are normally used in the FRP field. So we can see here, stress strain, the Sika products generally brittle. You move into the araldites over here, and finally to the typho, the strain, the elongation increases. There's a plateau forming on the araldite and the typho. So more ductile epoxies there versus more brittle for the Sika. So typical properties for araldite 420, the tensile strength, elastic modulus, and ultimate strain. So the ultimate strain of the epoxies are much greater than the FRP and also timber. Typical failure modes for the externally bonded and the NSM. So here are mode T. We've called this timber to adhesive in the timber. Now this is a really common failure mode for FRP to concrete, where we have a failure in the concrete, and we see this also with the timber. Part B here is the mode I, which we call a timber to adhesive in the adhesive. So this would occur in cases. We would attribute this failure mode to a stronger substrate that we would see more readily in hardwoods, and in cases inadequate surface preparation or application of the FRP. And we observe this now and then in EB and NSN systems. Ideally, mode T is the preferred failure mode. Why? Because we can relate the strength of the bonded interface to the strength of the timber. The fact that the failure is occurring in the timber. And we can determine the strength of the timber using existing tests. This is also the same preferred failure mode as in FRP to concrete. Failure in the concrete layer, we can determine the properties of concrete using standard existing tests, pressure and strength, and splitting tests. FRP to steel is a different case. We normally expect the failure to occur in the adhesive. We're obviously not going to get a failure in the actual steel, and we would prefer the failure not be at the steel to the adhesive interface. But a cohesive failure in the adhesive layer, then we can translate the strength of the FRP to steel joint to the properties of the epoxy. And finally, with FRP to masonry, we would expect to see the same failure mode as FRP to concrete, FRP to timber, and that is in the masonry layer. Other failure modes we observe for timber, a combination of failure in the timber and failure at the adhesive, and in some cases we saw a wedge failure, so that's what we've got in point D there. These were less common failure modes. We also witnessed adhesive rupture in the EB, and this was a case of the epoxy not being fully impregnated into the fibers. So that's why we were very, very careful on the viscosity of the epoxy that we used. We wanted something with a lower viscosity that could be more easily impregnated into the fibers. In the NSM case, we actually ruptured the FRP in cases. Now, a fundamental behaviour here is the influence of the length of the bonded FRP. Now here we're comparing a so-called side A and side B, and we're applying a wet layup FRP to softwood. We're using it in a Sika 300 here. It had sufficient viscosity to enable it to be worked with the sheets. So wet layout. Now, what's the difference between side A and side B? This is something really interesting. We can see here the circular growth ring patterns. Now, side A, and depending on how the timber section is cut, but we're always going to have a side where the growth rings intersect the side at the predominantly right angles, 90 degrees. So that's our side A. Side B, over here, is where the growth rings roughly parallel to the face that the FRP is bonded onto. Now we can see here the open squares refer to side B and the closed side A. First of all, we can observe that as the bond length is increased, the strength of the joint increases until we have a leveling off. That means we've reached an effective bond length of around the 100 millimeter bond length mark. So that means if we increase the bond length beyond 100 millimeters, we're not going to see a noticeable increase in strength of the joint. Now, this behavior has been observed with FRP to concrete a lot over the years, and we see this same behavior in FRP to timber. What else can we notice from this plot? Well, the scatter in the results. And you'll see that the scatter for our side B specimen, so our open square, is much smaller than the scatter that we're seeing for the closed squares that bonded to side A. Now, what's causing this? Well, for side B, we find the dominant failure mode is in the timber, and it is between the growth rings. For side A, the failure is occurring more at the interface, and it's generally more at the timber to adhesive interface. This is attributed to the higher strength, you could say, of that surface versus the lower strength, or the lower strength between the growth rings of the side B surface. So we can ask ourselves the question, what is the bond strength between growth rings in timber? And that may give us a good indication of the bond strength of the joint. That's a good topic for future research. And that's really a timber topic all in itself. But from here, we can see that the lower bound of the strength, particularly at the higher bond lengths, rests with the side B. Less scatter, a more predictable failure result, given that the failure is in the timber. Okay, let's move on and look at another case. So here we've applied FRP, extruded plate this time, to hardwood and also softwood side B. We can see that there is less scatter with the side B. It's the open shape, but the filled-in shape is there's still scatter. And it's the same phenomenon that was occurring on the previous slide, with the hardwood creating more failure between the FRP and the adhesive versus the softwood failing within the growth rings. Here we've varied the type of adhesive. So 6 different types of adhesives. We're looking at either protruded or wet layout plates applied to hardwood or softwood side B. And on the vertical axis, we've plotted the efficiency. So it's the measured peak strain versus the strain capacity of that. Our first 2 results for each epoxy type are the application of FRP to hardwood. We can see there's not that much change between the epoxy types. Okay, for the 420 epoxy gives us a higher efficiency for the wet layout plates. The failure mode for the hardwood is predominantly uniform, and that's at the FRP to adhesive interface. Now the second 2 results for each epoxy type are the application to softwoods. And here there's also not too much variation between efficiencies and epoxy types. So that's because this failure mode is reasonably consistent of being in the timber between the growth rings. Nonetheless, from here we can draw conclusions what would be the more suitable adhesive types for bonding extruded or wet layout plates to hardwood or softwood. In this plot we observe the effective bond length concept. So 30 is quite a short bond length, 150 is a long bond length. With the effective bond length being around the 100 mark, we can see that for 150 long bond length, that we have this sort of plateauing of slip. Once we've reached the load capacity of that joint, the effective bond strength. We're not quite at the joint capacity for our shorter bond length with FRP. Again, this is behaviour that we would exhibit in FRP to concrete. Now finally, this corporate of 4 slides, there's quite standard results that we can produce where we have strain gauges positioned along the length of the FRP. The top left-hand corner, we can plot the load versus the slip. That's the slip at the free end. The top, let's say the bottom left-hand corner, the distribution of strain along the length of the plate as we increase the level of the load. Bond stress in the upper right, and the bond slip. So the bond stress slip exhibits a similar shape to that of FRP to timber, and FRP to concrete, and also that FRP to masonry. And for the modelers out there, it's the bond slip behaviour which is really important for defining the constitutive law between the bonded interface. So in light of this, we can develop the constitutive laws, which I won't show here, but laws can and have been developed which can then be incorporated into numerical modelling. My presentation today is predominantly of an experimental nature for you to understand the trends. In the interest of time, I won't go into this in too much detail, but these are the results from the NSM. I just want to highlight the bottom left-hand corner. The efficiency of the NSM is 60%, and for the same type of epoxy, plate, timber, the difference between NSM to EB, there's an efficiency factor of 2.5. So that is, the NSM joint is 2.5 times the strength of the externally bonded joint. And this is a common phenomenon for NSM systems. For the NSM, as we increase the bond length, we can see that the strength of the joint also increases. And we also see the effective bond length phenomenon for short and longer lengths of FRP in the NSM. Okay, there's some fundamental behaviour and a test program around EB and NSM FRP in timber. How do we translate that to the design of beams? Well, we tested a series of beams, glue laminated timber, tension face plates, either externally bonded or NSM. So on the left here we have an externally bonded FRP plate, and on the right here we have an NSM plate, and this is actually failed from the bonding test. Now, taking into account theory that has already been developed, so studies of Dai, or studies led by Dai, Ueda, and Sato in 2005, and also Zhou, Wu, and Yun in 2010, we can extract parts of their models to develop our own. So we've developed the strain capacity model here, or this is the strain that will cause debonding as a function of the plate thickness, elastic modulus, and bond length. And also as a function of gammas, gamma T. So here's the type of the wood, whether it's a softwood or hardwood, side A, side B. The type of the epoxy, gamma E. Adhesive 420, typho versus the Sika. And so that's a reflection on the ductility of the epoxy. And also, if we're dealing with a joint or a beam, we have a different lambda factor here, and these are best fits. So these have been calibrated from our joint tests and also our beam tests. And so here is showing how the strain capacity model compares to the test results. So we use a selection of test results for calibrating the model, so training data. We also had a lot of test results that were not used for calibration, but that we used for testing. So a reasonable average of around 1 and a standard deviation of 0.26. So there's still a reasonable scatter in results. Nonetheless, it's a start. There's a framework's been developed. Researchers out there, if you want to build yourselves a database and refine these models, this is a pattern of research which has been followed for bond strength models for other materials, such as concrete, steel, and masonry of FRP. Finally, we can design a timber beam using a standard sectional analysis, constitutive model for the timber, and this is one we've assumed here, so it's linear elastic, and then we have a yielded portion for the compressive part of the stress strain response. Plane section assumption, with the key being the limiting strain between the FRP and the timber, which is captured by this formula here. This will allow you to design a timber beam which is strengthened in flexure with either an externally bonded FRP plate or a near surface mounted. Okay, that concludes this part of the lecture around joints and beams. Now, in my remaining time, I'd like to say a few words about another research project, and this is the application of FRP to frames, in particular moment-resisting frames and moment-resisting joints. So the research question or the motivation to investigate the strengthening and repair techniques for moment-resisting timber joints with steel dowels. So for an application to frames which suffer from seismic attack. So at the program of research here, which was from another PhD project, the student conducted single bolt joint tests with various FRP configurations around the bolt, 2 moment-resisting timber joints on the bottom left-hand corner. Once we had those test results, we calibrated numerical models, so hysteresis modeling applied to nonlinear static analysis and nonlinear time history analysis. I'll just show you again the experimental work just to give you a physical feel for the problem at hand. Photographs of bolted timber joints. So these are obviously newer structures, and the motivation for this work being for older structures. A bit of a revision, how joints or bolted joints can fail, whether they're shear or double shear joints. Our moment-resisting joints we tested as double shear joints. Now, existing repair strengthening methods for bolted timber joints, so whether it's resin injection, laterally inserted screws, steel plates, densified wood, or glass fiber fabrics. We're now looking at the application of FRP, and so here are some techniques which we tried out. So epoxy repair around a bolt hole that had been locally crushed. 2, the application of externally bonded FRP and near surface mounted FRP. If it's a historical structure, then the NSM can be embedded in timber so you won't see it. But some logical arrangements of the FRP. So if the load is acting horizontally, a longitudinal direction, we've got here the case that the FRP is supporting that bolt, you could say, as it's being pushed through the timber, whether in an EB or an NSM mode. Here is our test setup for our bolted moment-resisting joint. We've got 4 center bolts here. They're in double shear, and the joint is connected at the top and the bottom through a series of bolts that is then held in the bottom in the reaction frame and the top through the the actuator. Glulam joints designed in accordance to Eurocode 5, displacement control loading. Now, we tested a series of undamaged joints that we applied externally bonded, or NSM FRP, and we also damaged some joints, and then we repaired them. We repaired them with epoxy infills around the damaged joint hole, and then with either EB or NSM. So these are retrofitting applications as well as repair applications. The properties of the timber, the tested properties are shown here, as well as the properties of the FRP, the epoxy, and also the steel dowels, all from testing. Load in a displacement controlled manner in accordance to the British standard 12512. Failure modes are shown here. Mode J, a standard failure mode for double shear timber to timber connections. And in figure B here on the right, the joint opening and the joint closing and where the crack patterns will form. Now, if we fail a joint, that means the bolt has been pushed into the timber, so there's local yielding and crushing of the timber, and we can reinstate that joint by gluing in epoxy wedges. Epoxy wedges can then form, can fail again by being pushed into the timber. More failure modes, and as we would expect, as the bolt is pushed into the timber and it locally bears onto the FRP, there's a local bearing failure. Here, and in cases we can have even a cutting into the FRP. These are hysteresis responses. Here are a couple of externally bonded configurations. So this is at the 45 degrees to the grain direction, and this one over here is at 90 degrees. We can see that we're getting a bit more strength or moment capacity out of these this arrangement here. And we're also getting more capacity and even more deformation or rotation out of the epoxy repaired plus with the EB arrangement. This is a very brief snapshot. There's obviously a lot more of this data which we can show to get a better feel, but I thought this plot could capture the essence or the rough effectiveness of each of the repair techniques. So in terms of the energy dissipation, we can see that this externally bonded scheme is, and as well as this NSM scheme, so where the FRP is perpendicular to the load direction, that is providing the most amount of energy dissipation. And we would say that would be the most effective for seismic retrofitting applications. We also tested steel plates and other configurations, which I won't share here. So in conclusion, these last 45 minutes or so, a very brief overview of a few years of research, and just from my team. There's certainly other research out there in the open literature, and perhaps some of you are already conducting your own research in this area. But we've conducted fundamental research on the behaviour of FRP to timber bonds, the failure modes, the effective bond length concept, and the development of a bond strength model. We then apply that to the design of FRP strengthened timber beams. And then we look at another project on the application of FRP to moment resisting timber frames, in particular moment resisting timber joints. This is a research field that I would say is not that well developed, in that there are not many people researching in this field. And as I said at the beginning of the presentation, it's a really ripe field to do some really good research in. What should happen next? A framework is being developed here, and others are developing their own frameworks. We need researchers to compile database, someone to go through the test data, and from that database out there to develop models, calibrate them so we have more confidence in the models. And then we need to test more beams, more structures to verify those models with. And really, what I've talked about here is a whole lot of testing. There's a whole numerical world out there that can do with more exploration. Timber, as itself, is a notoriously difficult and variable material. And there have been researchers out there over the years conducting numerical modelling of timber on its own. We have conducted some modelling, and there are others out there who are modelling FRP to timber. But with more reliable models, constitutive models for the FRP to timber bonded interface, we would expect more reliable numerical studies to be performed. So if you're a historian on the research attached with, say, the FRP to concrete, we can see a lot of similarities or a way forward for research on FRP to timber. A lot of the same techniques, but let's not forget timber is still fundamentally a different material to concrete. So there are also a lot of unique behaviours that we could expect to see. A couple of the PhD projects I've referred to, a journal paper, there's also conference papers out there that we've published, and there's papers under review. And this is also an ongoing research topic for myself and others around the world. So with that, I'll draw this presentation to a close. I hope it's been helpful. It's given you an introduction, or for those working in this field, you've got something out of this. Please feel free to contact me with any questions, information. Very happy to follow up. But I hand it over to you. Any comments or questions you'd like to make, please post in the chat box, and I'll try and answer it. Any questions? Anyone working in this field or designing in this field? Okay, if there's no questions, maybe the presentation was very clear. Again, I hope you've enjoyed the session, and I look forward to some sort of communication in the future. All the best. Bye for now.